Yeah. Well, you gotta be careful because I could have said, no, Jeff. Right? Sometimes in evil. Individuals commute, parentheses associate. Do you see what I mean? What moved here? Parentheses, that's associate. Parentheses associate. What moved here? Individual vectors. Okay, that's commutative. Because like you and I were individuals, we commuted to get here. Right? You weren't born here and just you stay in this room. Hopefully. I don't know. It's a weird story I think I would have heard by now. That was true. That guy that was born in that room that wasn't even made before he was born is weird shit. Sorry. That's not useful, Jeff. All right. Oh, okay. These other properties are just not interesting. This is good. But this is interesting. Now that we've identified I, J, K, if I have this vector, considering what I said earlier about building blocks, I can actually write that. And real quick, I want to make sure. Can somebody tell me what I's name, the full component name of it is?
1, 0.
Beautiful, because it's all along the x-axis and so forth, right? All along the watchtower or something. So you could deconstruct this, but do I really have to go that far? How would you say, what is this vector in terms of I, J, and K? 4I minus 2J plus 5. Okay, all right, no big deal. You guys see that? And sometimes there were problems that's easier to do when it looks like this, and sometimes there are problems that are easier to do when it looks like that. And that's why we have multiple ways of representing something. I like it. But that kind of denotes the idea of the building blocks. If I could define a three-dimensional space where none of my axes are perpendicular to each other. And there are, believe it or not, situations where that actually makes something easier somehow. Right? In which case, I still want those these guys, to be unit vectors so that they can build off of them the way that I'm used to. Right? So the idea of unit vectors is good because it helps me create these building blocks. And this is the exact building block idea I was talking about. That builds this. Oh, so here's a really neat question. Take this vector. You guys try this out right now. This should be relatively simple. Let's see what happens. Find the unit vector in the direction of this vector. Let me call it U. U. And it's not going to be pretty, but it's going to be something. So if you're not sure where to start, just remember, how do you create a unit vector? You always do the same thing. Why is this not currently a unit vector? Its length is not 1. So don't try to memorize too much. If I ask you for a unit vector of anything, you pretty much always do the same damn thing to it. All right. This is one of those you get it or you don't situations. So what do I have to find first to be able to do this?
The norm.
The norm, the length of this thing, right? So what's the length of U? Square root of 45. Cool. I like it. Which, yes, what is that? Don't make it a decimal.
3 root 5.
3 root 5. I love it. Oh, no. So when in doubt, give me exact. Don't give me 0.21 rounded, no, give me exact. So then what's this going to be? What's the unit vector going to be? Unit vector in direction of u is going to be u divided by the length of u. So all it does is preserves the direction u is pointing, and it just shortens it or even lengthens it if it's less than one length. So it's actually pointing in the same direction, just length of one. So you get 4 over this, so it'll be end up being 4 rad 5 over 15. Is that cool? Rationalize, oh shit. Negative 2 rad 5 over 15. And 5 rad 5 over 15, so rad 5 over 3. Is that cool? Is that cool? Can you all shake your head like that? Okay, makes me feel better. Alright. Cool. Not too bad, right? Almost, you're like, okay, wait, I'm worried. This makes too much freaking sense. Where's the weird ass bullshit? That's coming. Not bullshit. No bullshit. What's up?
Are we doing dot and cross today?
Yes, we're going to get into dot. It's my favorite stuff, too. I don't know if we're getting into cross, because there's a lot of stuff to get into there.
Never planned it early cross.
I understand.
I can't believe what the stuff on the
15, 15, 3.
Wait,
Oh, rationalizing. So like 4 over this, multiply rad 5. Yeah, cool. I like that. Okay. So I think we've covered just about everything in 12.2. Yes, cool. I like it. Yep, cool. Now, you know, part of this course is lecture a lot. Oh well. I am going to have, thank God, some handouts and stuff for you guys to work on. So I won't always be just talking at you. But also, doing the homework and coming with questions, that's huge. Maybe sometimes I'll answer them. But no, I just had a feeling that a lot of you hadn't even tried it yet. I don't want to give too much away. But please, dear God, you've got to come in. So like, even though I'm done with 12.2 for lecture, we're going to talk about 12.2 with questions you guys come in with. So you've got to get in there and try that stuff out. So I do want to get into 12.3. There's a really cool, I want to put a link. I don't know if any of you's looked at the imaginary numbers YouTube video stuff I had up there, and you're all like, I don't have time for that. But it's a really cool link that further explains. You guys know matrix multiplication, right?
Yeah.
If I gave you 2 matrices right now, you could tell me if you could multiply it, and if so, you could then multiply it. Is that cool? That whole bam, bam thing?
Yeah.
All right, hopefully it makes sense. And I don't know how it was explained to you why it works that way. So the thing about operations like multiplication and all that, we can define it in a way that makes the most practical sense. So the funny thing about vectors is we're going to discuss 2 different definitions of ways to multiply vectors. Okay, sure. And that's just because there are at least 2 ways that actually have practical use. And they both involve multiplication somehow. But realize that there could be more than one way to do it, because these are not just numbers. These are collections of numbers. And they have more meaning than just a symbol number. They have direction to them. They have magnitude to them. So there's all these different things that can come into play. So that leads us to more than one way to define multiplication. So one example I like to start with kind of leads us to one definition of dot product, and then we're going to brute force math the other definition of dot product. So here we go. This is kind of a strange situation, but just go with me. I wanted to make a physical situation that leads to an idea of dot product. So this is the best I can come up with. And I don't want to... Dot product has physical interpretations that we'll get into later, but I'm just talking about how to even describe what dot product itself does. All right, here we go. Let's say that I had this crate, and I'm going to pay you, now just go with me, this is very strange. I'm going to pay you $8 a foot for every foot you can push this crate in that direction. You with me? So if you push it this way, because it's easier for some reason, I ain't giving you shit. I don't care if you push it that way 40 miles, right? I'm like, oh, nothing for you. But you can push it this way and still get some money, or are you kind of with me? Does that kind of make sense? And I know this is very contrived, but too bad. I just want something a little more physical. You can imagine this. This is just some weird dude with money, so what the hell, I'm going to do this shit. Why not? I need some money. And you notice that it's pretty heavy, and in this direction, it's like all pebbly shit, and it's like, it's not good. It's very difficult. But you notice there's like, in this direction, there's kind of like this, it's supposed to be straight, nothing crazy. Yeah, that's better, sure. In that direction, you notice that there's kind of like a groove that it will just go along. It'll be easier that way. You with me? It's nice and smooth, and whee. So hell yeah. So that means I'm going to push it farther than I'm going to get paid for, of course, because I'm not going to get paid for any Y component of this. Are you with me? Okay. So let's say this is I haven't drawn it this way, but it doesn't matter what it is. This is 60 degrees. I'm not going to let it go unless I make it more. All right, 60 degrees. And let's say that I push it 10 feet in that direction. Are you with me?
Yeah.
So how much money am I going to get? That's the question. This is a problem you can figure out. It's a pre-calc level problem. So do it. How much money will I get? So I pushed it 10 feet that way. Don't say anything out loud.
I was just going to ask you something. Oh, sorry, I didn't see that.
60 degrees, yeah. Thank you.
That's
Yeah, this is the x-axis,
Okay.
and that's 60. I didn't even say it was, but if I were you, I would make that the x-axis. Right? Doesn't even matter, really. Don't say anything. Sorry. Don't say anything. I was apologizing for being so like, don't say anything. You're like, come on, man. I got the answer. It's not a difficult problem, but I love the fact that the formula comes right out of this. Would you agree that this is a multiplication problem? In a very direct kind of sense, or indirect in some ways? It's a trig problem, exactly. All right. So, what approach did you take? What do you have to find out first, of course?
How far it went.
How far you actually went in the x direction. So how do you get that? So the x direction motion, that's the only thing I'm going to get paid for, right? So what? How much did I move in the x direction? Yeah, how did you get that? You did 10 cosine, crazy, because cosine likes x, right?
Yeah.
Did I already do my rants about SOHCAHTOA? Okay, I won't do it again. Soak my what? All right, 10 cosine 60, of course, is 1/2 because it's far away from the x-axis, so it's going to be the smaller one because cosine likes x and it's away from it. It's all scared. Whatever sticks in your head. So it's 5. I love it. So I want 5 feet in the x direction. So then how much am I going to get paid? $40. 5 times 8, $40. So it is fundamentally, it's a multiplication problem. So this is a form of multiplication. But it's multiplication dependent on direction. And doesn't that kind of make sense that a form of vector multiplication needs to have that idea in it because vectors are based on direction, right? All right. This is not a complete explanation. It isn't, because it's almost impossible just to explain it, period. You have to couch it in something. So what did I really do here? I did, let's call this, what do you got, Jeff? I don't know, dude, just say something. This is U, this is V, and this is theta. So how did I actually arrive here? I'll be really careful. I'm being a little bit evil because I said U equals, but that's U, and I shouldn't say equals. Because what would that actually be? That would be the
Magnitude.
The magnitude, I love it. Okay, so I was being a little bit evil, but we'll be all right. So I'm going to call, this is actually the dot product of these. And how did I arrive there? I took the magnitude of V, right? The magnitude of V, and I
Cosine theta.
multiplied by cosine theta, and then I took that and I multiplied it by the magnitude of U. That's okay. That is the definition. One definition of dot product is that. I like that example. I can't remember actually how I came up with it. It's the same example I used 5 years ago now. I'm like, where did you come up with that pass, Jeff? Oh, well, too bad. I love that. Now let's do another one. This is going to be the brute force math approach. No made up shit. We're just going to directly attack an interesting situation. So, let me see if I remember which way. Okay, good. So I'm going to redraw my situation here. There's my V, there's my U, there's my theta. How did I want to do? Okay, good. What is this vector here? See if who remembers. Come on, you can do it. Beautiful. U minus V. How do you know it's U first? Because it's pointing at U, right? Let me stop there for a second. You're going to love this. Sorry. What kind of triangle is that? Is that any special kind of triangle? Especially because theta is just theta. Is it right? Are you sure? No. Like, the angle could be 90.0002 degrees. Nah. But this is just any triangle. I know I'm trying to represent it here, but I didn't even define any of the other angles here either. I don't know what the other angles are here. So I don't know what kind of triangle it is. So how are the sides related then?
Law of cosine.
I love it. Law of cosines, right? So what would that... Stay with me now. Stay with me now. What, Jeff? What the freak? Trust me. Or don't. I don't care. Just don't leave and you'll eventually go, I should have trusted that guy. So in general, if I have a triangle, let me just... what do you got here, Jeff? Let's call that C. Sure. And this is the angle between them. It's not Pythagorean, of course, right? It's related to Pythagorean. What's the adjustment that I have to make? Now look, that's how I remember it. You just start with, the side that the angle is across from is the main side, right? So you start with Pythagorean and then you adjust it with this. The two sides and the angle between them. That's how to remember that easily. Thank God I'm telling you how to remember it easy, because you have to remember it. Right? You have to know it. You have to be able to bring it up, dredge it up whenever you need it. So, take a minute and write for this triangle what that looks like. Stay with me now. This should be your bread and butter. You should have what I call math stamina. Can you not only write... And one quick little thing I want to point out. This is a little bit... let me not be evil. What does C here really represent? No. I mean, just in general, what would C be? Give me an example of what C would be. Give me a second.
Displacement?
No, not really. Well, sort of. Depends on how you mean. It's just a number, right? It's a scalar. A scalar is just a number by itself. A vector is a scalar plus direction. Are you with me? So it's purely scalar. So when you go to put, for example, what are you going to put here for this triangle? And the what of U minus V? The length. So the length of U minus V squared equals. Okay. So it's that length thing you have to make sure that you throw in there. You with me? Because it's the lengths of the triangles that are related. Lengths of the sides. This is really cool. Just do it. Some of you guys are looking dubious. Some of you guys are... You can even just draw a duck. I wouldn't even know. I just see your pencil moving. Makes me feel better. But maybe try it out instead of a duck. I don't know. Howard the Duck, though. We are defining something that is as fundamental to vectors as multiplication is to everything that came after it. So this is kind of important. This is huge. So that's why I want you to be very intimately involved in the construction of this. Let me put it over here. Let me take you away. I'm not going to use it. You guys can finally see everything. And you're like, I don't want to see it. You still going? Yeah. All right, I think he's going to take a break here in a minute. So then this would be, doesn't really matter, but like v squared, right? Plus then u squared minus twice u v cosine theta. Is that cool? All right. I don't know if anybody tried. Let me say this. I don't know if you tried to go further. I'm sorry if you did, because I'm going to say these are in 3 dimensions. Let's just make it the most general that we want to right now. So tell me, if it's in 3 dimensions, how would you identify the vector u, considering that you don't have any specific information about it? You have to identify 3 components for u. So what do you think is the best way to call these then? Well, remember you got to do v also. So maybe, how about u1? You could do that. Just a little. Let's call them u1, u2, u3, v1. I made you all think you had a choice, but oh. You have no free will. So, let me see how far you can make it. You could do this. You could do this. So what's u minus v? Just to help you out, just a little bit. Blah, 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 right? All right. And you know, now what's beautiful about this is, this would be the square root of u1 squared plus, but isn't this squared? So no square root. That's nice. Right? Okay, maybe. You gotta love that. It's not nowhere near as ugly as it seems. A lot of shit's gonna cancel very quickly. It's gonna become a very small, little, beautiful thing. Almost too nice to believe. Have faith, have faith, have faith. So for example, won't this be v1 squared plus v2 squared become a v plus v3 squared? Yeah, sure. Right? And then of course that's going to be use. Use, guys. And actually, I tell you, leave this like it is. Don't replace the u and the v with stuff. Just leave it like it is. Trust me. That'll be directly related to. In fact, what does that look like it's related to that we already talked about? Well, what do we have so far for u dot v? U, v. So what is this? U dot v, holy shit. Okay, so that's what we're doing. We're trying to figure out another representation for dot product. Because I can't always find the angle between 2 vectors easily. So I need to have another way to do it. Yes?
How is the magnitude of v squared the same as... Oh wait, never mind. I found my own answer.
Oh, cool. All right. That's just the sit back and wait approach to teaching. Okay. All right, plus u1 squared plus u2 squared plus u3 squared. Let me just go ahead and write this as minus 2 u dot v. Is that cool? Of course it's cool, because that's what the hell it is, right? Now what about this side? Again, I really want you guys, is everybody cool with the fact that that is that easy? That's all it is. Because to find the magnitude, it would be the square root of blah, blah, blah. So now there's no square root. So don't make too much out of that, right? To find the magnitude of any vector, you just add the squares of the components of the vector. It's beautiful. Right? Square rooted normally, but here's squared, yay! So here, what's the first component of this? u1 minus u. So this is going to be u1 minus v1 squared plus u2 minus v2 squared plus u3 minus v3. You can do it, Jeff. Now, please, you guys notice, I mean, you should know how to FOIL very quickly, right? So aren't you going to get u1 squared, u2 squared, u3 squared? v1 squared, v2 squared, v3 squared? And then a bunch of cross terms? Is that cool? And the reason I want to write like that is because then all this shit's going to cancel, right? You guys see that? So I can collect the first parts and the last parts and the middle parts. What would the middle part be here? 2 u1 v1, right? So then you're going to get the same kind of thing, minus 2 u1 v1 minus 2 u2 v2 minus 2 u v3. u 3v3 equals this. So that is everybody pretty similar to this one. You could all do this again if you want. That's gone, that's gone. Divide by -2, right? So you get u1v1. Is that cool? Divide by -2? Because you get that equals this now. So u1v1 plus u2v2 plus u3v3 equals u dot freaking v? What? What? All right, now watch. This is why I can only do dot product. It's already 35 after. It's crazy. You guys see that? It's cool. I mean, that's cool. Let that be cool. Realize what just happened. We just found a reason for this besides just, complete this triangle and, if it's law of signs, you gotta watch out for the asshole thing. Whatever. Remember those days? The ASS is what we call SSA, but we call it ASS. So you remember it's the asshole that could swing and it has two possible. And I forgot to check for the signs. So you remember those days? So I can do that well because I remember what my students looked like as we were doing. So now watch what this means. This is almost too good to believe. Let's do a two-dimensional one. A two-dimensional one, guess what? Yeah, like that, right? So let's do a two-dimensional one because I can find the angle between those easily. Do you understand? I really want you to understand this. The first dot product definition required me to know the angles between the vectors. If I have three-dimensional vectors, I have no good way to find the angles between them. Now I do. We just created one because there's two ways to get the same number. Therefore, I can always calculate this. Shit, it's just multiplying components together. So look at this. This is a little bit freaky. This is very straightforward. This totally makes sense as a candidate for multiplication of vectors because it's multiplying the components by each other. That's almost too nice to believe. So what if we had the vectors, what, Jeff? I don't know, Jeff. 3, 4, and let me just keep everything in the first quadrant. 1, 1. All right, a couple things I want you to do. First, calculate the dot product using that. Then, calculate the dot product using that and show that they're equal, which means you have to find the angle between them, which you should be able to do. Or at least the cosine of the angle.
What's that symbol between the 2 points? It's just like the and.
I'm sorry? Oh, and. Sorry, yeah. So find the dot product both ways and show that they're the same. Do this. So again, that just means it would be this equation, right? And so how do you find the dot product? 3 times 1 plus... All right, fine. Now finding the angle between them, that might be the challenging part, but it really shouldn't be. No. I gave you one that was nice and the other one's not. You might. It comes up, but you might not. You don't have to know it. But you can represent the cosine of the angle very easily. You see what I mean? You just need the cosine of the angle, right?
Oh, yeah.
So I think people could very easily make too much out of this. It is a 3, 4, 5 triangle.
Yeah.
So you have the cosine. All right, what do you get this way? 7. I was like, what the hell? All this shit and for 7. But good. This is a very easy example. 2 dimensions, not really ugly. It's very simple. So we get u dot v. Let's call this u and this v just to v, just because. Equals 7. Notice, when I take the dot product of 2 vectors, the result is what kind of thing? A scalar. So that's why we have to have another, that's not why, but we do have another way to define multiplication of vectors so that the result is itself a vector, which kind of the idea of closed. Do you know what I mean when I say closed? Don't say, the door is closed. Do you know what, like, the real numbers are closed over addition? Which means anytime you take any real numbers and you add them, the result is still a real number. You don't go outside of the real numbers. So there are situations where you have, like, positive integers are not closed under subtraction. That's a really easy example. 7 minus 8, oh shit. It's not a positive integer, so too bad for me. You guys with me? So having a multiplication operation defined so that two vectors multiply to still be a vector is kind of nice. That's a closed kind of thing. It remains the same type of thing at the end. But this also, it makes sense. So this is nice. We have scale. This is also called a scalar product sometimes.
Because the answer is a scalar.
So here, does anybody get the cosine of the angle between these two? What you got to do is, here's the 3, 4, right? I don't know. Jeff, you could do better. Jeff, you could do better. Sure. Here's 3, 4. So what's that angle? And then 1, 1, what's the angle for 1, 1? 45. So here's 1, 1. Woo! And what's the angle for, I was making it easier. Too bad. You can still figure out the angle. What's the angle for 1, 1 is 45 degrees. What's the angle for 3, 4? Well, you do actually need to go further. You need the inverse tangent of 4/3. Are you with me? You can actually just, so how are you going to do this? Well, what's the length of u? What's the length of u? 5.